Так, а есть ли звук? Звук? Да, звук есть. So let's continue our discussion of Noetherian and Artenian modules. So last time we finished with the following observation, that if we take a short exact sequence, then the module in the middle, so M is, say, Noetherian or Artenian, if and only if M prime and M double prime are Noetherian or Artenian respectively. So what that means, well, in more naive terms, it means that if you take, say, for example, a Noetherian module, any submodule is Noetherian, any quotient module is Noetherian. So this is immediately follows from this observation. Now I want to derive a corollary from this proposition that we proved last time. This is the following statement. So if you have a finite family of Noetherian or Artenian modules, then the direct sum is again Noetherian or Artenian. So if Mi, where I is running between 1 and n, are Noetherian or Artenian, the proofs are the same. So then the direct sum is Noetherian, Artenian respectively. So easy but useful observation. So proof is relatively simple if you already know this fact. We just consider short exact sequence of the following type. So for example, you take M1 and then you embed M1 as a direct summand into the sum of all these modules. So I running between 1 to n, sum of all mi's. And if you embed this M1 as a direct summand, what happens if you take the quotient? Well, it will be the same sum, except you start summation from 2, right? So the quotient is the direct sum where I is running between 2 and n, mi. Now, if you just look at this short exact sequence, everything follows by induction. So M1, say we want to show that the sum is Noetherian. So M1 is Noetherian. So we know that this is Noetherian by the induction hypothesis. So by the short exact sequence and the previous observation, this module is Noetherian. So that's the end of the proof. Okay, so I also have several other observations. Okay, so if ring R is Noetherian, again, maybe Artenian, then any finite R module is Noetherian or Artenian if the ring is Artenian. The proof is again just one line. So if module is finite, well, it means that it has finitely many generators, but equivalently you can say that there is a surjective map from the R to the N to this module. Right? Now, if I know that R is Noetherian, remember that a ring is Noetherian by definition means that if this is Noetherian as a module of itself, so this sum is again a Noetherian module by the previous observation, so the quotient of a Noetherian module is Noetherian. And the same for Artenian. So again, the short diagram is the whole proof of this statement. And another observation, which is completely elementary, but still it's useful to notice this. If R is Artenian, then any quotient ring is Artenian. Or Artenian respectively. So I don't need to prove this because actually it's just a special case. It will be just this quotient when n is equal to 1. So if you have an Artenian ring, we can construct quotient. This is again Artenian, so that's a way to construct a lot of examples of Artenian modules. Well, Artenian rings, actually. Okay, now let's discuss briefly. So this is next section 4.2, Artenian rings. So we define Artenian rings in such a way that ring is Artenian if this is Artenian as a module, but of course by one of the theorems that we proved last time, ring is Artenian if and only if any ideal I in this ring is finitely generated. Right? So we saw that one of the ways to characterize Artenian modules was to say that any submodule is finitely generated. So submodule of an R, this is by definition an ideal. So any ideal is finitely generated. Now let's prove the following famous theorem. So theorem, this is called the Hilbert basis theorem. So this says the following: if R is an Artenian commutative ring, so then the polynomial ring in one variable over this ring R is again Artenian. Okay, so let's prove this. Now we need to take an ideal in the polynomial ring, and I'm going to do the following induction construction. So I'm going to construct a series of ideals. So I define ideal I0 so to be just the zero ideal, and then I'm do the following. I take say fk in the ideal I minus the ideal ik minus 1. Right. At the moment I only defined I0, so I can define what's f1. So f1, this is just the any polynomial, so polynomial of the least degree. And then I can inductively define these ideals ik to be ideals generated by f1, f2, up to fk. Now let ak be the leading coefficient of the fk. So meaning that I can write this fk as some a k x to the dk, and then I have other terms, and these other terms maybe have smaller degrees than this dk. So this is the leading term, and this is the coefficient of the leading term ak. Now J is an ideal in the ring R generated by all these AKs. So I know that R is an Artenian, so this J is finitely generated. So I can as well just write this is generated by A1 up to some AN. Right? So I know that among these generators, I can choose a finite set of generators, but well, maybe I need, say, for example, A2 and A100. Then I just add all these generators from 1 to 100. So this n is just the largest number that I need to choose to get all the generators. It's just convenient to use these generators. Maybe I don't need all of them, but at least this gives us convenient formulas. Okay, so this J is finitely generated, and this is one of the possible set of generators. This means that if I consider the leading coefficient of the polynomial with the index n plus 1, I can present this as a finite sum with maybe some coefficients Ri of these AIs. Since an plus 1 is an element in this ideal. Okay, so then let's define the following polynomial. So let f be the fn plus 1 minus the linear combination with coefficients Ri of all the previous polynomials fi. So I is running between 1 and n. And I also want to multiply this by the x to the power dn plus 1 minus di. So what I'm achieving if I'm considering such difference? Well, look at the leading terms. So here the leading term will be an plus 1 x to the power dn plus 1. Now here when I take this combination, this linear combination with coefficients Ri, so the leading terms of fi, well, this is just some AIs, and exactly when I take this sum, I'll get this coefficient, an plus 1. But now it might be that the degree is wrong, so I'm multiplying this thing. So this thing kills essentially this, instead of if I start with fi, which is ai x to the di, when I multiply by this thing, right, I'm killing this power, and instead of this di, I'm getting dn plus 1. So this sum, the leading term of this sum, is exactly this thing again.
Sorry, can you explain why an minus n plus 1 lays in J?
By definition, J is something that's generated by all these coefficients A's.
Yeah, and why n plus 1?
All of them.
Okay.
So it is defined as countably generated ideal. And since the ring is an Ethereum, it has finite set of generators. Okay, so, and notice, by the way, the way we constructed this thing, this makes sense because this number is not negative. So, so what we can see is that the degree of this polynomial f is strictly smaller than the d n plus 1. So this means that f is actually an element in the ideal In. But if you just look at this combination, maybe move this sum from the right hand side to the left hand side, we can conclude that fn plus 1 is again in the In. And that's a contradiction with our construction. Right, so maybe I need to say that I'm starting with ideal I, which is not finitely generated. Then I get this contradiction.
So we got contradiction with something that fn plus 1 is least degree.
Yeah.
Least degree.
Yeah, so by the definition, the degree of this, well, how to say this? This contradicts the procedure how we choose these fn's. Okay. So this theorem has an important corollary that says the following. So if R is Noetherian, then any algebra of finite type, any, say, R algebra of finite type, is Noetherian. The proof is again just one line. So what's an algebra of finite type? Well, it means that we consider polynomial ring infinitely many variables. So let's say this any R algebra A. So A is the quotient of this polynomial ring by some ideal. But we know that polynomial ring in one variable is Noetherian, so by induction in any finitely many variables it will be Noetherian. So, and we also know that the quotient of a Noetherian ring is Noetherian, so this thing is Noetherian ring. And this give you some reasonable family, sufficiently large family of Noetherian rings. You start with a ring that you know that it's Noetherian, for example, a field. Any field is Noetherian, or maybe integers. And you construct some polynomials, you take some relations among these polynomials, and you get Noetherian rings. So maybe if you want to think about Noetherian rings intuitively, well, you think about this as the rings of this type. Maybe over field or integers, or maybe over some more complicated Noetherian rings. So the Hilbert basis theorem has a variation, which I'm not going to prove, but at least I want to mention this theorem. So theorem, if R is Noetherian, then formal power series ring over R is Noetherian. So you can think about this theorem as an exercise. Can you modify the proof? It will be a little bit harder than the proof for polynomials, but this is still true. So proof is exercise. And another theorem that I want to mention, and the proof again is an exercise, and maybe we even do this exercise on the seminar. So if any prime ideal is finitely generated, then R is Noetherian. So this theorem is due to Cohen. It's Cohen is one of the famous commutative algebraists. So if you study things like complete rings, maybe we'll have time in this course to study complete rings. Cohen proved the structure theorem for complete rings. So he has several very interesting and useful famous results in the commutative algebra, proved around 70 years ago. Okay, so maybe we'll do this on the seminar, but this is again exercise. So I hope that we will have time to do this. So this is one more indication that prime ideals in commutative algebra plays a special role. So for example, if you want to check that the ring is Noetherian, you have to show that any prime ideal is finitely generated. Okay, and that's all I want to say about Noetherian rings. So next section, 4.3, modules of finite length. So definition. So first of all, suppose that an R module M has some kind of filtration. So R module N has given a series of submodules so we're going to assume that first submodule M0 always coincides with the M. Then inside this M0 there is a submodule M1. Well, maybe in some cases it could coincide with M0. And we just continue doing this, but we need to finish after finitely many steps. And the last module has to be the zero module. So Mn has to be the zero module. So this is kind of finite filtration with n steps. So now the first part of the definition. So given two sequences or series, two series for two modules. So I have a two series for one module. So I have one such thing, and then maybe I have another such thing. So again, I start with a zero. Now let's call maybe this n m. So two such series, one I call n, one another I call m. And then we can say that, so the second is a refinement of the first if H mi appears in the second. So this is one module. So essentially the idea is you start with module, you find such series of submodules, and the refinement is just the largest series in the sense that you can maybe insert more modules in somewhere in between. So this is the first part of the definition. Now, second part of the definition, two series. Maybe let me give them a name. So again, as before, I call one series with n, and the other series for m is called n. So two such series are called equivalent. Well, if you have the following, so the first requirement is that the n is equal to m. They have the same length. And the second requirement is that the quotients are the same, maybe up to a permutation. So there is some permutation sigma in the Sn such that quotient mi modulo mi plus 1 is isomorphic to the quotient n sigma applied to I modulo n sigma applied to I plus 1. Zero series?
Yeah, I'm just confused with that statement. Suppose that our module n is given zero series of some modules. How do I understand this?
It's A, so it's not.
Oh, A series. sorry.
No. Okay. So, and the last part of this definition, a series is called a composition series if all quotients mi modulo mi plus 1 are simple modules. So this is for I starting with 0 and ending with n minus 1. Now when we finish with this long definition, I want to say this is definitely not a new idea. You've seen this when you discussed group theory in the algebra course, right? We definitely discussed, well, last year we definitely discussed the composition series for groups, for finite groups at least. That was a sequence of subgroups such that all the quotients are simple groups. So here you require that these are simple modules. And of course, simple module means, if you don't remember the definition, it just means that there are no non-zero proper submodules. So all submodules here are just zero and the module itself. Okay. Now we have a little technical lemma. So lemma, this is called sometimes Zassenhaus lemma. So now we assume that we have a module. So L is an R module. And in this module, you have 4 submodules, such that M prime is a submodule inside M, which is a submodule inside L. And you have another 2 submodules, N prime sitting inside N, which sits inside L again. So for these 4 submodules, you have the following 2 isomorphisms. So M prime plus M intersect with N. And you need to take the quotient by the M prime plus M intersect with N prime. So first of all, this is isomorphic as a module to the M intersect with N, quotient by the M prime intersect with N plus M intersect with N prime. And now the second isomorphism is the same as the first isomorphism, but up to a change of notation. So this is isomorphic to the N prime plus the intersection of the N and M. And I need to take a quotient by the N prime plus N intersect with M prime. So usually when people formulate this lemma, they just keep this step in the middle, and they formulate that this left-hand side is the same as the right-hand side. But if you just add this step in the middle, it actually immediately tells you how to prove this. If you want to prove that these 2 things are isomorphic, you just need to prove that this is isomorphic. And if you have a proof for this part, the proof for this part is exactly the same, because this is just the same thing up to notation. Well, and if you formulate it like this with the middle term, it actually almost tells you how to prove this. Right, so for example, I want to prove this first isomorphism. Now I definitely have a map. So if I take M intersect with N and the quotient by the M prime intersect with N plus the M intersect with N prime.
Can I ask a question about the definition of equivalent series?
Mhm.
Could it be so that, for example, sigma of I is greater, sigma of I plus 1 is less than sigma of I?
Yeah, it could be any permutation. It could be permitted. So
So it could be just 0, because it would be submargin anymore. Like, it would be like vice versa, you see? Like, it could be so that then the N set.
no. Of course, we want this to make sense. We want this to be that this thing has to be a submodule here. So we only consider such permutations.
Yeah, I mean, it feels like we should put N
Ah.
sigma of I modules and sigma of I plus 1. Like,
But that's what I meant. I wanted to permute the quotient module, so maybe that's not just a good notation for this. But how to write this in terms of the sigma, I don't know. Maybe I just take it back.
you could add 1 after permuting the I. Yes, we do.
Okay, let me just do this. I just say this in words. I take this back and mi modulo mi plus 1 are isomorphic to n, maybe j modulo n j plus 1 up to permutation. But what I want to say is that you have one such series, you have another series, so maybe the modules are different, maybe the quotients, if you just compute them step by step, are different. But for example, if you get some simple module in the beginning of the first quotient in the first sequence, it will be somewhere, maybe at the very end, as the quotient in the second series. Okay, so back to the proof of this little lemma. So I start with this module and I want to construct a map. Let's call this map phi to the quotient on the left hand side. So what is this map? Well, I think, no, that just, is this right? Yeah, so it looks to be that I correctly written these two terms. Okay, so what's the definition of this map? Well, you take a representative in the intersection, you take the class with this representative, and then this map phi sends this to the class with the same representative. But you consider a class modulo the submodule m prime plus m intersect with n prime. And this is about defined map. So maybe get like this. So this is well defined. Since we have the inclusion of the m prime intersect with n plus m intersect with n prime, well, this sits inside the module m prime plus m intersect with n prime. Right, so then there is a standard argument to showing that this is whenever you have a such map which changes, keeps the representative but changes the classes, well, it's always well defined if you have an inclusion like this. Right, so for example, take two different representatives, right, x and x prime. The difference will be in this submodule. But if you look at the difference, because the difference is in this submodule, it will be also in this submodule. So these classes also coincide. So that's about the defined map. And I claim that clearly this map is surjective. Right? Because whenever I study classes here, because I consider them modulo m prime plus this thing, right? If I have a representative, say m prime plus m double prime, right? So that's a representative of something here. I can as well just forget about this m prime because this is in the submodule here. So this is equivalent always to the m double prime. So an m double prime is in this intersection. So any class has a representative where this first component is just 0 because I take a quotient by the m prime plus something. So it means that if I has a representative here, x, well, I just use the same representative here. So this map phi is just clearly surjective just because we have m prime and m prime. So well defined, clearly surjective. So the last step is to check that this map is actually injective. So I want to see that the zero, sorry, that the kernel is 0. Okay, so what's in the kernel? So I start with some class again, and if this class is in the kernel, it means that this representative belongs to the m prime plus this intersection. Right, so this is what we have in the kernel, representatives that are in this sum of two modules. But I claim that we have the following inclusion of modules. So if you take m prime, intersect this with n, plus you take m intersection with the n prime, then this sits inside m prime plus the intersection of the m and n prime.
Yeah, you have it there. So well defined. It's the same.
Oh, sorry. Yeah, that's just the wrong formula. That's already something that we know. The formula that I now need to show that this has a trivial kernel is the following. So if I take the intersection of the m and n, now what I have in the kernel. So that's a representative, and if I want this representative to represent something in the kernel, so I want this to be in the intersection of the m prime plus m intersect with n prime. Right, so this will be exactly classes, so representatives of the classes which will be in the kernel. Right? But now I have the following inclusion. This is contained in the module m prime intersect with n plus m intersect with n prime. If you just look how these modules sits inside each other, you'll get this inclusion of modules. But this means that if you start with some representative that give you something in the kernel, it's actually a 0 element to begin with, because this belongs to this submodule. And the representatives, well, representatives that are in the submodule, these are zeros. So this inclusion implies that the kernel of phi is 0. So we prove this little technical lemma. Okay, now I want to do the following. I want to erase the proof, but I want to keep the lemma. So the next statement requires some space to write and prove. So if you don't have any questions about this, I'm going to erase the proof. So the main reason why we want to prove this lemma, well, it's not very interesting isomorphism theorem, but we need this to prove the following important theorem. So this is the Schreier's refinement theorem. So, and it says the following, that any two series, so one is called M for the module M, and another is called N. So any two such series have equivalent refinements. So it means that if you start with any series, well, another person starts with another series, if you just add more modules, then they become equivalent. So proof. Well, I just define new modules. I say by definition that the module with two indices now, I and j, is the module M with the index I plus 1 plus the intersection of the mi intersect with nj. And I consider this for I running between 0 and n minus 1 and j between 0 and m. So, for example, you can notice from this definition that mi0 is exactly the same thing as mi, and also mi plus I minus 1, m. If you apply the definition, this is again mi. So then we have the following refined series. So I start with the same mn, which is just 0. By definition, this is the same thing as m with the index n minus 1 and the second index m. Now I use this new module, so this will be an increasing sequence of submodules until I reach m with the index n minus 1 and 0. So the first index is fixed, and I'm only changing the second index, and you can see that I have embedding of submodules. This again follows from this definition of mij. Now, I already noticed that mn minus 1 and 0, this is the same thing as just mn minus 1. But mn minus 1 is the same thing as mn with the index n minus 2 and m. And then I just repeat this procedure by decreasing the second index until I reach m n minus 2 and 0. And I just continue doing this, right? So in every row I'm changing the second index, and when I change rows I change the first index. So the last row, if I do this, will be m1, which is the same thing as m0m. So again, doing the same thing, I'll reach m00, which is just m. So that's the refinement. I added a lot of modules. So I started with the sequence of the length n, and now this is a sequence of the length n times m. So that's a huge series, or huge sequence of modules, and I can do the.
Is it necessary that refinement is the length of the refinement is always a multiple of the initial length? Can you just
No. No, you can just add one additional module.
Okay.
So you could go from n to n plus 1. So in this particular procedure, just the refinement that n is multiplied by m. So I'm not saying that, for example, in this procedure all the modules are different. Maybe there are a lot of these embeddings, maybe just equal modules. So. So, and then you could do the same thing for the second series. So, the same procedure. For the second series, so we almost proved this. So where you just say that nji is n with the index j plus 1 plus nj intersect with mi. Now let's look at the quotients. Mij, you take a quotient by the mi j plus 1. Now, if you write the definition, this will be mi plus 1 plus mi intersect with nj, quotient by the mi plus 1 plus mi intersect with nj plus 1. Here I'm just using two definitions. So this definition for the two indices. Now, next step, this is where I need the lemma. So I'm claiming that this quotient is isomorphic to the quotient nj plus 1 plus nj intersect with mi, quotient by the nj plus 1 plus nj intersect with mi plus 1. So there are no mistakes on the blackboard. This isomorphism up to changing of notation should be exactly the isomorphism of these two things. Now, and the last step is just to notice that this quotient is exactly nji quotient by the nji plus 1. Again, you just need to plug in two definitions.
Why is mi 0 equal to mi? Well, it should be clearly equal to mi plus 1. Mi plus 1.
You're asking about this formula? Well, let's look. Mi 0, right? So this means that the index j is equal to 0. So here we have n0, and n0 is just the module. So this intersection is just mi. So it, yes. So this is actually the end of the proof. Yeah, this is the reason why we need this lemma. Okay. So let's derive an important corollary, and this is again a theorem that has actually a name. So this is Jordan-Holder theorem. So any two composition series are equivalent. So notice that, notice that this actually immediately follows. It doesn't require any additional proof. Well, that is because if you have a composition series, all the quotients are simple modules, so it means that it's not possible to refine the composition series. So it means that any refinement of a composition series is just the same composition series. And if you take two composition series, they have equivalent refinements. It means that actually the given two composition series coincide, or equivalent. So coincide up to permutation. So that's the proof of this theorem. It follows from this computation with the Sassenhaus lemma and the Schreier's refinement theorem. And that's maybe the main reason why we're even interested in such computation with quotients. So another remark is that if you look at the proof, we never used that the ring is commutative. So this statement definitely works for over any ring, not necessarily commutative. And even more, what you really need to prove this, well, you need to know how to intersect sub-objects, how to take sums. So for example, if you want to prove Jordan-Holder theorem for groups, this is the proof. You don't really need to change anything except you assume that all these letters represent groups. So this theorem of Jordan-Holder was mentioned in the first year algebra, but without proof. So that's the proof. And that's the reason I decided to insert this proof in the course, because maybe you can just give you the statement and ask you to believe the statement, but at least in some algebraic course, you need to see a proof. So this also gives you something that you learned from the first year algebra. Okay, now with this.
How do you define sum in general? It's like the group span divided these two groups.
Yeah. Yes. Well, you can for groups you probably can take just.
Just clear, in which way group is a module? Is it like a module?
Group is not a module. The sum in the group theory, this will be just the situation where you have two subgroups and you can multiply them inside the group. So that is what was, say, KH.
Is it KH or KHHK?
No, just KH. So this is analog of the sum operation. So in general, this is just a set. It's not necessarily a group, but for example, if you have property like this, then you can actually prove that KH is a subgroup. So this is true, for example, if one of the subgroups is normal, etc.
Is this lemma right for just sets?
For sets, I'm not sure about what the operation path is supposed to mean.
Maybe so.
Okay, so with these fundamental results, we can see that the following definition is actually makes sense. So definition, a module which has a finite composition series is called a module of finite length. So the length, there is a special notation for this L, R of M. So the length of this module, so a module M, the length of such module is the length of a composition series. So we need this Jordan-Holder theorem to actually say that this notion of the length is well defined, doesn't depend on the composition series. Okay, so how this notion of a module of finite length is related to what we've discussed. Why this subsection about finite length modules is in the chapter about Artenian and Ethereum rings, Ethereum modules. Well, that is because we have the following proposition. Let me just for shortness, instead of saying this in words that the module has finite length, just write that the length of R, length of M over R is finite if and only if M is Ethereum and also Artenian. So finite length modules are modules that both Artenian and Ethereum. Proof. So let's start maybe with the finite length module. Okay, so first observation that any simple module is Artenian and Noetherian, right? Because in a simple module we don't have any change of submodules. All the change are trivial change consisting only 0. So these conditions for Artenian and Noetherian are clearly satisfied. Now, for general module finite length, we just can do this by induction. Because, for example, we have M1 that sits inside M, right? And then we have a quotient M by M1. So get a short exact sequence like this. So where the... Okay, maybe I want to start with induction from the other direction. Okay, so there's a short exact sequence like this, and this is the first short exact sequence, and the last short exact sequence will be the following form. So this will be mn minus 1, which is embedded into mn minus 2, and the quotient is mn minus 2 modulo mn minus 1, and maybe not this is the last one, but maybe the last one is the following. I have 0, which is embedded into 0, meaning mn, but this is just 0. And this is embedded into mn minus 1. The quotient is again simple, but the quotient is just mn minus 1. So since this is 0. So in any composition series, the first term is 0, mn is 0, but the next term is the simple module. Because any quotient is, we assume any quotient is simple module. Here this is quotient by 0. So this mn minus 1 is simple module, so it will be Artenian and Noetherian. Right, so then we have this module, which is Artenian and Noetherian. This module is simple, again Artenian and Noetherian. So the module in the middle is Artenian and Noetherian, and then you just go back up on this row. So you get this, for example, that m1 by the induction will be Artenian and Noetherian, and this quotient is simple, so m is Artenian and Noetherian. So this is the proof in one direction. Now, let's go in the other direction. So now I want to assume that this module is Noetherian and Artenian, and I want to construct a composition series, which is finite. So let M1 inside M be a maximal proper submodule. If this is maximal, then the quotient is simple, right? This is the correspondence theorem. But there is a question why we have a maximal submodule. So we know that we have maximal ideals in the ring, but why we have maximal submodules in the module?
It's the same by some level.
Well, do you know examples where there are no maximal submodules? No, the answer for this question is yes. The real question is, do you remember the example?
Well, any ring that doesn't have any...
Remember that we defined the proof group, which was Artenian but not Noetherian. So in the proof group we classified all the subgroups. And among the subgroups there were no maximal subgroup. So there are modules without maximal submodules. And why we have maximal submodule here?
Oh, because it's Noetherian, I guess.
Yeah, that's exactly the reason. In Noetherian, you remember that one of the characterizations of Noetherian modules was that any subset of modules has a maximal element. So here you take a subset of all proper submodules. So of course, my maximum module will always want something that which is not equal to m. M is not the maximal submodule. So M1 is a proper maximal submodule. It exists because the module is Noetherian, and this is where we use the Noetherian condition. And then I'm just continue doing this. So I construct this. Well, maybe this is not a good idea because it looks like, well, I don't know. It looks like I'm changing notation. So all my previous definitions, I started with the index n. Now I'm starting with the index 1, but I guess you can understand this. So now I'm just continue doing this procedure. I take a maximal, well, M1 is a submodule in Noetherian module, so it's again Noetherian. So it means that I can apply the same argument for M1 and find the maximal submodule M2.
Why M1 is Noetherian?
It's submodule. Well, you missed the beginning of the lecture. So in the beginning, I went back to the short exact sequence.
Prime is submodule of it,
Yeah, so this sequence tells you that any submodule of Noetherian or Artenian modules, Noetherian or respectively Artenian, are the same for quotient. So you do this procedure, and you get this. This is descending sequence of submodules. Now let's use that M is Artenian. So this descending sequence of submodules has to stabilize somewhere. Right? But I'm claiming that in fact if you do this, you can say that Mn is 0.
because there's no any max proper submodules.
Yeah, because in this case you get that you have a submodule such that maximal proper submodule coincides with this module. So this is only possible for a 0 submodule. Yes, so this is the finite composition series. Again, all the quotients are simple modules because we choose always maximal submodules, and the quotient by maximal submodule is a simple module. Okay, now I want to prove a very natural property of a lens. So next proposition. For a short exact sequence, we have the following. The length of the middle term is equal to the length of the first term plus the length of the last term. Of course, you're supposed to read this as follows. If the length of the m prime and the length of m double prime is finite, then the length of the m is finite and is given by this formula. The proof is actually quite simple. You just choose a composition series so take some composition series for the m prime, right? And then take a composition series for the m double prime. But by the correspondence theorem, I can say that all the submodules in the m double prime look like, well, some m double prime, m modulo m prime, and then m double prime 1 modulo m prime sits inside m double prime. So the fact that I can write all the submodules in the m double prime, which is just the quotient of the m by the m prime, in this way, well, just follows from the again from the correspondence theorem. And now what I'm doing here, I'm just gluing together this composition series and this composition series, where I just remove all the quotients. I just look at the m double prime m, right, which is the same thing, because this is 0, this is the same thing as the m prime, as a submodule here. So I just
M1 double prime quotient by M prime is less.
so m double prime, but the shortness of this exact.
M double prime 1, it's just some models in M double prime, yeah?
So this is the same as the way it's written. They are submodules in the m double prime. Any submodule here is of this form. Some submodule in the m quotient by the m prime. This is the correspondence theorem for modules.
So M1 double prime is a module in M.
M1 double prime is a submodule in m. That's correct. And then all you just need to take one composition series and combine this with another composition series consisting of this.
Yeah, and the first sequence series is should end in M prime. Yes, M prime.
Yes, thank you. Yeah, this is a composition series for m prime. And we need also, I don't know, the statement that under this correspondence the quotients are preserved. So I guess this is second or third isomorphism theorem. So it implies that the quotients of this m primes without these quotients are again simple. But anyway, so I think this is a relatively easy proof. You can think about the details. Okay. By the way, you immediately get the following observation, that if you take any sequence, not necessarily 3 modules, but any number of modules, which is exact, then what would be generalization of this observation? Assume that all these modules have finite lengths. Is exact sequence of modules of finite length. How to generalize this formula? Yeah. The alternating sum is 0. That would be the general formula. And maybe you already have seen something like this in the topology when you discuss an exact sequence of vector spaces. Anyway, so of course the proof of this formula just immediately follows from this formula. You just need to take this exact sequence and split this into the short exact sequences, several short exact sequences, and you prove this by induction on n. Okay. Now let's, for a minute, return to the general situation of Artenian and Ethereum modules. So proposition. let F be an endomorphism of a module. So let M be an endomorphism. And then they have 2 observations. So first, if M is Artenian, there is such positive n such that the image of the f to the n plus the kernel of the f to the n is equal to m. In particular, if f is injective, then f is bijective.
Also, if f is surjective, then f.
Yeah, well, I can say that this is surjective, I can say this is bijective. That's the same statement.
Yeah, okay.
And there's a dual version for Noetherian modules. So if M is Noetherian, again, there is such positive n, such that the image of the Fn intersect with the kernel of the Fn is equal to 0, and in particular, if F is surjective, then F is bijective. So this second in particular part is not very interesting for us because we know that this is not just for Noetherian modules but for any finite modules. We derive this from the Nakayama's lemma. But for symmetry, I decided to include this. So I'm going to, by the way, is it clear what notation Fn means? This is just the iteration of the F. You just apply, say, F squared, you just apply F to the F of something. Right? Just the iteration of this map. So, in special case, if you just work with vector spaces, then this will be just powers of matrices. So I'm only going to prove the first part, and the second part has a dual proof, and I'll leave this as an exercise. So proof of 1. Okay, we need to use the fact that M is Artenian. Well, we can use this as follows. We consider images of F. Right, so we have image of F, and inside image of F, we have image of the F squared, etc. So this is the descending sequence of submodules. I think you can immediately check that image of the F squared is inside the image of F, and the same is true for all powers. So there is a stabilization. So there is n positive, as promised in the proposition, such that the image of the f to the n is equal to the image of the f to the n plus 1, etc. So I claim that the following is true. For any x in the module M, there is another element y in the module M such that f to the n of x is equal to the f to the power 2n of y. Well, it just follows from the stabilization, whereas use the fact that image of the fn is the same as the image of the f to the 2n. It will be convenient to have this 2n here. So now I do the following thing. I take x and I write this x as fn of the y. And then what I need to do, well, this is in the image of the f to the n. And then the second summand is just fn, no, this is just the x minus f to the n of y. Right, to prove this formula, I need to present any element of the module as something in the image of the f to the n and something plus something in the kernel. Well, in this formula, this is definitely in the image of the f to the n. Right? But also, the second summand is in the kernel, because if I apply f to the n to this element, I'll get f to the n of the x minus f to the 2n of the y, which is 0.
Can you explain why for any x there exists such y?
This is from the stabilization. Starting with n, all the images are the same.
Yeah.
So as I take something in the image of the fn, it has to be something in the image of the f2n.
Yeah.
So I'll just continue the stabilization and I reach f to the 2n. And this is just a convenient choosing of the numbers. So with this n and 2n, I can write a formula like this, and you see that this is in the image and this is in the kernel. Okay, so we proved this formula. How about the in particular part? Do you have any ideas how to prove this?
Isn't this kind of obvious?
Hmm?
Isn't this kind of obvious?
Why this is obvious?
Kernel, the power of f is contained is equal to 0, since kernel of f is 0. Therefore, image of some power of f is equal to
Yeah.
module.
Yeah, so if you start with an injective endomorphism, right? So the kernel of this is trivial, and the any powers is still injective, right? So the kernel of this thing is also trivial. So you see that m is equal to the image of some power of f, right? But because image of some power of f is even, well, it sits inside the image of f, and it's already coincide with the m. So image of f has to be equal to m. So it's indeed kind of trivial if you know this formula. Okay, and the proof of the second part is, again, you just need to look at the kernels. Kernels again give you some chain module with Ethereum, so do this. Maybe we do this on the seminar. Okay. What if we combine these two properties together? Now, then we get the following corollary, which is also has a name. This is sometimes called Fitting's lemma.
It's a name.
Yeah, this is the name of another mathematician. So, if, as before, f is an endomorphism, of a module of finite length. Finite length. So then what we can say, well, module of finite length is Artenian and Ethereum together. So we have this and this together.
Yes. So if such n exists, then any n that's greater than this n is true. Is also true for this.
Yeah, I think so. Yeah.
It's true. Yeah. Then for the theory.
Well, there is n where the images are stabilizing, and there is maybe another n prime where the kernels are stabilizing. So maybe you want to choose maximum of these two n's.
Yeah, but if we don't know that for any.
If you just want to work with just separately Artenian, I think it's true, but I'm not 100% sure. Maybe that's a little exercise.
Since every time we through the high power kernel gets bigger, it must be true.
Mm-hmm.
Since image is stable and kernel gets bigger.
Stable, so
Yeah.
kernel is bigger.
Okay.
So it's
Yeah,
true.
so it's true.
And for the second part.
The same, I think, works. Yeah, but the point I was trying to make, if you take a module of finite length, you know that this is true, and you know that this is true.
Yeah, but you want to take some n
Mhm.
that's maximal from this and this.
Yes.
If we don't know that
Yes.
for n prime is greater, if
I know that there is a sufficiently large number n such that this is true and this is true, and this n is the same.
okay.
No, this is larger than the n that comes from this part and the n prime that comes from this part.
Oh, okay.
But if you have these two properties, this exactly means that I can decompose m into a direct sum. So then there is such positive n such that m is isomorphic to the image of the fn plus the kernel of the fn. Okay, so next corollary. So every non-nilpotent endomorphism F of an indecomposable module M of the finite length is an isomorphism.
What is indecomposable?
Now, indecomposable means that, let me write it here. Maybe I insert definition before this corollary. So a module M is indecomposable if M is not isomorphic to a direct sum of two submodules. So if you can present module as a sum of two submodules, then this is decomposable. If this is not decomposable, this is called indecomposable. So for example, any simple module is indecomposable, clearly, because there are no submodules. But the converse, of course, is not true in general. Indecomposable. Okay. So the proof is again not very hard, because in this case we just know that M is the image of the Fn plus the kernel of the Fn, right? And since the module is indecomposable, we have two options. We have that the image of the Fn is equal to 0 and the kernel of the Fn is equal to 0, right? So one of these two possibilities has to be realized, otherwise we get a decomposition of the module. But if the image of the Fn is equal to 0, this means that this is, so F is nilpotent, right? Now we have the other option that the kernel of this Fn is trivial, right? So then this means that Fn is isomorphism, right? Because if there is no kernel, this module has finite length, and in particular this is Artenian and Ethereum. So if in this case we use that Fn has trivial kernel, so this is injective, hence this is bijective. So I guess in this case it's enough to use this Artenian. So finite length is particular Artenian. So F to the n is an isomorphism. So the only thing we need to derive here is that F is an isomorphism.
Well, F has no kernel, since kernel of Fn
Yeah.
is equal to 0.
And again, the same thing. If F has no kernel, module finite length, in particular Artenian, so this is true. So you can, well, anyway, this is the end of the proof. And this is the end of today's lecture.
Кстати, не все происходит.
А там ремонт идет.